Welcome to lecture 3 of Introduction to Machine Learning with Python. And today it's Introduction to Neural Networks. So let's just head right in and see what all that is about. So artificial neural networks, as we call them, they are a machine learning methodology, which is it's a bit different from the ones that we have been talking about so far. And it's basically inspired, the architecture of these artificial neural networks are inspired by the biological brain. And so I'm no biologist, but here to the right, I put a picture of how sort of a neuron works in the brain. And basically it gets some input. So this is a neuron here. So it gets some signals, x1, x2, xn. And then something happens. So it has like some kind of pre-programmed response to the input signals. And then what it does, it sends an output to some other place in the body, for example, a sensor or whatever it could be, or even another neuron. And neural networks in the computer world is something much similar to this. So maybe you've seen figures like this, which kind of this is like a graphical representation of a neural network in a computer. And most often these nodes and these edges, they just basically represent specific mathematical operations. On the next slide, I'm going to introduce what these can be, some examples. And one of the advantages of having neural networks set up like this, so this left end is what we would call the input layer, and here we would have the output layer. You can have multiple inputs, you can have a single input, you can have multiple outputs or just a single input. One of the advantages of this is that you can model nonlinear functions. So for example, we saw how the linear regression could not model the sine curve. And with a neural network, you could, for example, you could model a sine curve. Maybe you also encountered this term called deep learning. Deep learning is actually not that special when you know about neural networks. So deep learning is simply when you have a neural network with more than 3 layers, including the input and output layers. So yeah, for example, this neural network here, if we coded this, would not be deep learning because we only have an input layer and a hidden layer and this output layer in the end. Okay, so let's look at some of the these. So I have the same figure here as on the previous slide, this neural network. So let's see what these connections means. And before I tell you all that, I'm just going to introduce some nomenclature. So last time when we talked about, for instance, linear regression, we had an expression like this. So y equals the dot product of w times b plus or times x plus b. So here in linear regression, for example, we would call this coefficient here or these coefficients, we would call that the slope, and b, we might call that the offset. In neural networks, we also have a lot of these linear operations, but just because of how people choose to name these, we call the W, we call the weights, and the B is what we call the bias. So it's just a little bit different way of saying things between the various machine learning approaches. So let's say we have this neural network. So let's, for example, look at this node here, and what does this mean? So you can see maybe there should be like arrows on all these lines going from left to right. So this basically means that this node gets some kind of input from these 5 nodes here along the lines that goes into it. And down here in this figure, I've put in like how this node works in this representation. So from each of these 5 nodes here, there would be an x value that goes in. So x1 coming from this, x2 coming from the second node, and so on until xm, which would be x5 here. So the first thing that happens is the input from the previous node is multiplied by some weight. Here it's called omega1, but I'm going to call it w1 everywhere. So bear with me. And the x2 will also be multiplied by another weight. So that will be the weight associated with this line here, if you can see it, and so on. So all the input, all the numbers that are sort of like input numbers, they get multiplied by each a weight that is associated with that. And then finally, you sum up everything and you add this offset, this b, which we call the offset or the bias here. So you sum up everything here, and then to produce some kind of output response from the node that is passed on to the next neuron. Then you put it through some activation function, and an activation function is usually it's some kind of function that mimics what you see in these real neurons. So basically, it's often you see a function that is either 0 or 1, so it's like switched off or switched on here. And then finally, you take the sum and you put it in your activation function, and that number, we can call it y here, it comes out. So the number y would come out here, and it would go into this node, and you would do the exact same operations here with another set of weights that were associated to all these lines here. Whoops. So, and essentially we could write our neurons mathematical operation like this. So here in the inner part, we have the input vector multiplied by the weights that are associated with the input vector. And then we add this offset or bias to it. And then on this linear sum here, we apply some kind of activation function. So let me just show you some of the activation functions, and then we can talk about the parameters after that. So here I just have like a list of some really common activation functions that are widely used in neural networks. For example, just a step function. So if the incoming number z here, phi of z, is less than 0, then it's the function is 0. And then if it's the incoming number is 0, then it's 1/2. And if it's positive, then it's 1. And there is a bunch of these functions. So like one that is -1 and then switches to 1. It could also just be a linear function, so one that doesn't change what comes out. Or they're like piecewise linear and sigmoid. So we're going to come back to these sigmoid functions. We're going to use them later today. So it's basically just a smooth transition between 0 and 1, basically. So it's like the step function, just instead of like having a discontinuity, it's just more smooth between switched off and switched on. And also this rectifier linear unit is also widely used. And I think there was in the second set of exercises in the Python intro code, you actually have to code this function yourself. Okay, so one question you might have to all this is, what are the parameters in my neural network? So if I want to fit it to something, which are the parameters I can like change? So for example, in linear regression and kernel regression, we had these, what did we call them? We call them regression coefficients, right? And here, and those are our free parameters in those regression models. And here, of course, the free parameters are the weights and this bias. So let's try and count how many weights we have, for example, in this neural network. So you can see, for instance, here, so this is our input layer, and we call this our hidden layer, and this is our output layer here. So you can see from the input layer, there are 5 nodes, and each node has 5 connections to a node in the next layer. So that means that there's a weight for each of these. So there's 5 times 5, that's 25 weights connecting these 2 layers. And the same thing here, there are 5 nodes connected to 1 node, so there's 5 times 1 here. So that means there are 25 weights plus 5, that's 30. So those are the weights, and then the biases. Yeah, and there'll be 1 bias for each of these nodes. So there will be 5 biases here and 1 here. So there'll be, I guess that's 36 parameters, if I'm not mistaken, in total for this particular neural network. So just like, when should you use, one question might be, when should you use a neural network, and what are the pros and cons for this? So yesterday when we talked about molecules, we talked a lot about like how to come up with good features for molecules, for example. And we had these this Coulomb matrix, and then we had this like evolution of the Coulomb matrix called the bag of bonds, where the features were even more refined, and it's supposed to work better. So let's say, for example, we have something like this. So a bunch of phases, and maybe we want to implement some kind of image recognition or something. What you could do then is like you could measure, for instance, like they've done in this paper, like the width of the eyes and like angles and distance and width of the noses and stuff like that. And then you could maybe come up with some kind of feature for a face, for example, and then you could like put that into your model, and then you could say, oh, this is a man and this is a woman or something. And that might work, of course. But the problem is then like, let me see if I can, yeah, what if we want to like extend our machine to like include a bicycle and then also an apple? So things where these features don't really work. And in that case, you sort of end up in a way where you can't like, there's no real similarities that you can like quantify necessarily between the different systems you have. So the solution to that is basically input the raw data to your neural network, and then like use the neural network to kind of learn how to represent and handle your data. I'm just going to show you an example from image recognition. Yeah, for example, for image recognition, one of the good performing image recognition neural networks currently is called VGG16. I guess it's kind of old after all now, but the way it works is basically if you have an image, you rescale it to some number. So you rescale it to 224 by 224 pixels, and then by 3 because there are red, green, and blue channels in pictures. And you're literally just in the neural network, you put those in. And then basically what happens is, what this VGG does is it classifies what objects it can see on the picture. And so basically you try to fit this very high dimensional with 224 by 224 by 3 features image. You want to like fit that to some kind of classification that comes out of your neural network. And what happens when you actually do this is that you can show that the first many layers, they basically learn how to represent internally the image, and then the subsequent layers and the final layers will be the layers that like use that sort of internal representation to actually make some sense out of it. So I'm going to go back one slide again, and this is from another neural network, also an image recognition for faces. And you can actually, so in this paper here, they've actually made some graphical representations of the first layers. And what they saw was that actually the first couple of layers ended up being some kind of edge detections. So these are actually images of the weights in the first layers. And then as they go deeper in their neural network, they actually find that they can like discover more and more sophisticated things. So basically, you have this very, very deep neural network with huge amount of parameters, where the first part sort of like discovers a good representation, and the last part should be some kind of good classifier or regression or something for the data that comes in. And now you can see with all these layers here, there can be a lot of parameters in your neural network. For example, this VGG16, it has 138 million parameters. So I think some of you might have taken Guido's course earlier this week and last week. And basically, what your task then becomes when you train this model is optimizing the weights. So basically, find the weights that give you the minimal error in the output. And then your task actually becomes minimize a function with 138 million parameters. So that's a one big task that you're faced with when you do neural networks compared to other more classical types of learning, where we actually had analytical expressions for the solutions, or we had a closed form solution to the optimal regression coefficients, for example. So yeah, how to optimize the weights. First, I'm just gonna tell you some more nomenclature that we use in neural networks. And one is called forward propagation. And that's basically, you put your data in the input nodes, and then you calculate the weights, and you go through the neural networks and some result comes out here from the output layer. Conversely, we have the backwards propagation, and this is often done using some. It's basically a way to handle partial derivatives. It's called backprop. So you will probably see this a lot if you read neural network papers or read about neural networks on blocks or something. And this is basically the opposite. So you calculate the derivative of the loss function with regards to the parameters for that given input that you could calculate the forward propagation of here. And so we talked about this yesterday, and we talked about this on Wednesday, like these loss functions we, for example, can calculate. So one that we looked at was called the mean absolute error. And it's literally just the absolute error for, so you take your input vector for a given system and you calculate what comes out. And then you compare that to the true answer. And then you can calculate the error, and you do that for your entire data set. Yeah, and that way you can calculate, for example, the mean absolute error and the root mean squared error is what we've been doing so far. And you could also do this, like, for example, if you wanted to do a classifier, you could calculate the accuracy. I think we looked at that briefly on Wednesday when we looked at the iris data set. We looked at the accuracy of our model in %, for example. Okay, so let's look at this backward propagation. So basically, what you want to calculate is the partial derivative of your loss function L here with regard to some parameter. And basically, so first of all, your loss function change in that comes from a change in the predicted value. So you predicted Y's, you predicted outputs. And you just basically use the chain rule all the way, like, and work your way back throughout the layer. And then in turn, your predicted output, that depends on your whatever activation function or whatever that is in your hidden layer. And then finally, your hidden layer relates to a weight that you had in your neural network. And then basically, you have to do this for every single weight and node and like track your way all the way back. So this is hugely complicated. But fortunately, I think almost any neural network code will use something called automated differentiation. And I think Guido also introduced this. So it's basically a way to define a function, and the computer can basically apply the chain rule itself and then immediately give you the answer. So you don't have to actually code all these crazy partial derivatives. And also for this type of neural network, these partial derivatives, they can actually be expressed in terms of matrix multiplications. And that means that if we run this on GPUs, which we'll do later, this actually it looks really complicated, and it looks like something that would be very expensive, but it actually becomes not so expensive. I wouldn't say cheap, but it's definitely something that you can do very, very fast for even very large neural networks. Yeah. So what are we going to do today? So the first thing we're going to do is we're going to code the most simple artificial neural network in NumPy. So I've showed you this function before. So it's y equals sine of x. And yesterday we looked at how linear regression could not fit this curve, but kernel-rich regression does work well. And today we're going to do the same thing with the neural network. So it's basically going to be the simplest neural network I could think of. So it's basically an input value, which is, that's going to be the x value. And then there's going to be a hidden layer here where we use sigmoid activation functions. And then the output layer becomes a sum that sums everything up. And then hopefully, if we optimize the weights and everything correctly, we should be able to predict some new points. So these test points are the red points. We should hopefully be able to predict that. So that's what we're going to implement. And after that, we're actually going to do, we're also going to implement deep learning on a GPU in Python. For that, we're going to use a toolkit called PyTorch. And it's basically the same data set that we looked at yesterday. So we're going to look at the atomization energy. So the amount of energy it takes to pull a molecule apart into its free atoms. And we're going to use this QM7 data set that I introduced yesterday. So it's like these small molecules where we have like, for a given conformation, we calculated with some quantum method called PV0, we calculated this atomization energy. So what we're going to do is we're going to take the same representations as we used yesterday, the bag of bond representation for these, and then we're going to feed it into this deep neural network that we're going to code. And then we're going to minimize all that on a GPU. So it's basically a more realistic neural network. So this is how you, if you were to implement your neural network yourself, I guess you can't see it because now there's a mouse over, but as it says here in the bottom, it's too complicated for NumPy. So we're going to do it in this PyTorch, which is a neural network framework that works on GPUs, and it also works in Google Colab with GPUs. And you can actually write neural networks fairly quickly using this. Okay, so let's head right into this simple artificial sine of x neural network. And yeah, of course, I made a Google Colab notebook where we're going to implement this. So again, we go to, let me zoom in a little bit. Whoops. Let me go to colab.research.google.com here. And go to GitHub and andersx /Python intro. So I'll just post this in the chat right away. If you want to open this on your own computer and do this simultaneously here. And then if you scroll down far enough, there should be a file called machine learning example sine of x here. So open this. So let's just run the first, run anyways. Maybe I'll full screen this and zoom in some more here. Yeah, so as we saw yesterday, we had this sine curve here. So this is the exact same code. I just literally copied it from the exercise yesterday, or the lecture yesterday. And on this sine curve, we have 10 points of training data here. So let's try and make a neural network model that can model this. So first, I'm just gonna define how we do the architecture. So this is what we call a fully connected neural network, and it has one input node, it has one hidden layer, and one output node or output layer. And the layer connections are these linear operations here. So it's basically xi are all what comes from the previous layers, and wi here is a weight that is associated with each of these arrows, essentially. And then we could also add a bias. So just because I want to make this coding exercise easier, I'm not going to include the bias. So we basically just set that term to 0 here. So I guess we already talked about how many weights there are in these neural networks, but let's just reiterate. So how many weights are there in this example? Well, basically each arrow corresponds to a weight, and here there are 5 arrows here and 5 arrows here, so there are 10 weights in this example. Okay, so the next thing we have to do is we have to select our activation function. So this is basically something you just have to do out of experience, and you have to like make some considerations if you want it to be continuous, or if you can handle jumps in your function. Then, for example, if your activation function has discontinuities, then you might not be able to make a differentiable neural network model, for instance. And so I just chose the sigmoid function, and the sigmoid function here I write as like sigma of x. One of the reasons that this is actually a popular function is because when you have to take the derivative of it, it has this kind of funky derivative. So the derivative of the function is the function times 1 minus the function itself. So it's actually pretty cheap to calculate this derivative of the sigmoid function. So what do we do in Python when we have a function? We define the function here. Let me scroll up a little bit. So now we have everything in the screen. So write def activation function, and then I call whatever comes in it a val. so some sort of value, and then I basically just say, I call it sigmoid equals 1 over 1 plus exponential of minus value, and then I return a sigmoid. So let's define this here. Okay, so the next thing we have to do is basically define the models. So we have to define each layer, like what happens in each layer, and so that's what I'm doing here. So our model basically, it starts with an input value, and the next thing it does, it multiplies. Maybe I should scroll. So it has an input value here, and then it multiplies that input value with a weight, and then puts it in here and multiplies it by another weight that puts into this activation function, and so on. So that's basically what I write here. So here I have a vector of weights. Here I just call it WIH. So it connects the input. So that's why I call it I, and with the hidden layer, so I call it IH. And the same thing for this here. That's the weights between the hidden and the output layer. So I call it WH for hidden, O for output. So the first thing we do, so let's look in the parentheses here, is that we multiply the input value with the weights of the hidden layers. So that's basically, if we put all the weights in a vector, we basically take care of everything that goes into each of these activation nodes here. And if our weights are NumPy arrays, if we then put that into a function, then the hidden, whatever comes out of this operation will also be a vector. So this will basically be the vector of what comes out of our hidden layer. The next thing we want to do is, in the way that we designed our architecture, is take what comes out and then put it into the next layer where we just sum up everything. So the last layer is like a sum operation here. So we take everything that comes out of the hidden layer, and then that vector we multiply by the next vector here, element wise. So remember, if you have two vectors and you use this asterisk or star operation in NumPy, then it's the element-wise product. So we do this element-wise product, and then we sum up everything, and that gives us output value, and then we return our output value. So this essentially defines our entire neural network, everything that happens here. Yeah. Okay, so let's first start and test the neural network with some random weights. So here I'm gonna select 10 random weights for the input to hidden layer, and 10 random weights between the hidden and the output layer. And I'm just choosing some random seeds. So if I run this again, I will get the same answer every time. And then I print the random weights, the two sets of random weights. And then I select some value that I want to test my system for. And basically my model, it's defined up here. So it's the input value, the first set of weights, and the second set of weights. And so I put the value 2.0, and then the first set of weights and the second set of weights. And then I save this in sign x predicted, and then I print the predicted and the true here. Of course, the true value would be mathematically sign of 2.0. Oh, I forgot to run this cell here. So let's run the next cell as well. And you can see these are some random weights. I just used NumPy to random to get them. And the predicted number is 3.8 roughly, and the true should be like 0.9. So obviously when we use random weights, it's pretty much random what comes out of it. So now we have to define, or we have to optimize these weights rather. Okay, so before we start, I'm just gonna set one parameter. So I'm gonna set the hidden layer size. So how many nodes? So on the picture, I had 5 nodes in the hidden layer, but let's set this to a very large number. So usually it's fine if there are many parameters in your neural networks. So let's set this to 40, which means we have 80 weights in total that we because we have like the input weights to the hidden layer and the output weights to the hidden layer. So we have 80 in total. So let's set this to 40. And yesterday we talked about regularization a little bit, so I'm going to talk about that a little more. And let's just set this regularization number to 0.01 here. And we can go back and adjust this later, actually both of them. So the way that we optimize the weights now that everything is set, so basically we want to find this best set of weights W that minimizes some loss function. For example, we can minimize the mean squared error. That's what we did yesterday. So we basically have the true weights and we have the predicted weights. This is actually the squared error. This is not the mean squared error. Yeah. So it's the true value and then the predicted value as a function of W. And you take that squared and you sum it up. Alternatively, to avoid that your weights don't go crazy, you can put this penalty on your loss function. So you have this lambda parameter we talked about yesterday, which is the same as this to L2 reg variable here. And then you just put your basically L2 norm of your weight vector here. Okay, so just like in the numerics lectures, we can use SciPy or NumPy to optimize these kinds of problems here. So now let's define our loss function as a function of a set of input parameters here. So that's what I'm doing in the next cell here. So our loss function should be a function of all our parameters, W. That's the only thing that goes into our loss function, essentially. And just to make things easy for myself, I only parse one vector of parameters in. And then here I split it such that the first 40 elements will go to the weights of the input to hidden layer, and the next set of weights will be the other set of weights here. So I just basically split it in half here. And this is just because the optimizer is easier to program if I only have one vector here. Then I do exactly what we did in the introduction to Python course. I set the square error to 0, and I run a sum over each of my training points. So these x's are from the sine curve. We had these 10, or it was 11 training points. So for each of those, I predict the value of y by running it through our model with the value of x, so the ith x, and the two sets of weights that we have here. And then I just add it to the square error here, squared. And of course, we could also do the same thing and add some kind of L2 regularization. But we're going to come back to that later. So now the last thing we do in our loss function is we just return the squared error here. So let's just run this cell and we define our loss function. Like that should be, yeah, I guess it's defined now. Okay. So one thing I skipped doing in this loss function is I didn't implement the gradient of the loss function. So it's going to be a little more difficult for the computer to minimize. But there are optimizers in SciPy that can work without using the gradient. They just do some kind of like triangulation where they do multiple points. So they basically they learn the derivatives by calculating multiple points, almost like if you do a numerical gradient, just in a smarter way, basically. One of these algorithms that are in SciPy is called Nelder-Mead, the Nelder-Mead optimizer. And it's implemented in SciPy.optimize.minimize object here, or module here. So basically from SciPy, .optimize import minimize. And then I set a random seed because I'm going to start from some random weights. And then I generate a vector of random weights. So remember we did this trick where we split the parameters in half just for practical reasons. So the size of my starting random weights are 2 times the hidden layer size. So they each can have 1/2. And what I do is I simply pass the name of the loss function and my starting parameters to this minimize function. And then I give them some extra keywords. So I tell it to use this Nelder-Mead method, which works without the derivative. And there are some other options. So I want to run 100,000 minimization steps. And this true just means that it should display some information about the convergence when it does it. And finally, so what comes out of this minimize function is an object or a dictionary called result. And basically, out of that result thing, it has a value called .x, and this .x is the set of parameters that minimizes the loss function, which is founded by the minimize function. And I split that in two halves, just like we did up in the loss function definition. And then lastly, I print them. So let's try and run this optimizer for 100,000 steps. So it shouldn't take very long, hopefully. It should take like 5-10 seconds last time I tried. Yep. And yeah, first of all, we get a warning that the number of iterations has been exceeded. So I think you can actually get true convergence if you do 200,000 steps. But basically, what happens is it minimizes the function, and then you're like almost converged. So basically, what you have at the end is actually a very good set of weights. So now that we minimize the weights, so I call these W final, the final like minimized weights here. Now that we have these, we can basically put them back in the model function that we defined before. So for example, for a value of 2.5 that we can put in and test our model with, we can predict sine of x by putting in this model function, we put the value, and then we put the input and the output weights in here. And then I just print what the predicted value, and I print the true value of sine of 2.5. And now you can see that's actually, it's pretty close. So this is seemingly not random, right? Okay. So it seems like we actually made a neural network that we minimized, and it actually produces some good results. So let's try and make a plot with pyplot here. And what I'm basically doing is just, I plotted from, I basically make all the points between 0 and 6.6, and then I calculate what the model is for each of those values. And that is what is plotted on the red curve here. And the blue dots are the training points, and the green one is a true behavior. So now you can see the neural network actually did exactly what I told it. What it did was it gave me a function that pretty much goes through all the training points, like we talked about. Unfortunately, you can see here to the left, there's some kind of, I guess if I remove this here, we can actually see the exact behavior. And this looks kind of funky. And this is a behavior you sometimes get out of neural networks that you have to like take a little bit of care not to avoid, or you have to take care to avoid it, really. And yesterday we talked about regularization, and we had this regularizer we added to the diagonal of the kernel matrix in order to keep a penalty on the regression weights. And basically, we can do the exact same thing for neural networks. So basically, if we go back, let me see, where was it? In the error function. So the error function we used first, it was like this. It was the error squared, and to the error squared, we basically add this penalty to the weights. So if we have larger weights, we can also have more crazy behavior in the neural network. And that's basically because if I go back to this figure here, so imagine you have some input and you put it through an activation function and multiply it by some number. If this number is very large that you multiplied by, then a small change in what comes out of your activation function, that turns up to be like, that can be a much bigger change to the value of your output function. So generally you want to like keep the parameters small in order to avoid these crazy behaviors. So for example, let's try and so let's enable the regularization. So let's comment out this one line and squared error here. I can see this will not work. So let me do it like this. So what I'm adding here, let's just remove these lines. So here is what we had before. And to that, I add the norm of the parameters, so the L2 norm, and then I multiply that by this this hyperparameter L2 rec here. Let's run this again. It ran, and then let's optimize everything again. So usually it's not so slow, but it's because when you run in the cloud, you just get assigned to a computer from Google that is free. So it could be a really fast computer, but it seems like today we got a really slow computer. Yeah, so these are the new weights, and I don't know if you noted, you probably didn't. I did. Some of the weights, when you didn't have regularization, they were like on the scale of like 10 to the power of 2, the largest ones of them. But now the largest ones that I can find are like, I don't know if there's 10 to the minus 1, but there's at least like 10 to the minus 0th order. So now at least we achieved what we wanted. We wanted the weights to be smaller. Yeah, so let's do the exact same plot again. Yeah, and now you can see we actually removed this crazy behavior, but it came at the cost of we said we want to minimize the function, but we also want to minimize the weights at the same time, and that means that we force it away from a solution that goes through all our points exactly. Yeah, and another thing you can also do, you can also adjust the hidden layer size. For example, if you have far fewer weights, that's also some kind of implicit regularization. So there are a lot of parameters you have to adjust in your neural network to get proper behavior. So the regularizer and the hidden layer size and how many hidden layers, it's definitely something that you need to tinker with a lot. I'm just gonna have a drink. Okay, so I hope this this exercise gave you a little taste of like how a neural network actually works internally and how everything is actually done behind the scenes. But now I want to show you something a little bit different from this. And the thing I want to show you is actually how to do or how to code something that uses a deep learning method and how that runs on a GPU. And I also prepared a notebook for this. So if you go to my GitHub again, andersx/Python intro here, you should be able to find something called machine learning example _ PyTorch. So let's open this here. Let's open this. And so before we start, so normally when you have these Google Colab, Jupyter Notebooks and Google Colab, what you get access to is a computer that has a little bit of memory and one CPU. But you can actually also get access to a GPU, which is, I think, really generous of Google. So to do that, you go to Edit, Notebook Settings, and Hardware Accelerator. So let's just check that we have that. So Edit, Notebook Setting, and this is already set to GPU. And then you press Save here. And then I'm just going to connect here. Okay, so the first thing I want to do is I just want to make sure that I actually have access to a GPU here. So I put some code in here. It's basically It's another machine learning or neural network code called TensorFlow, which has this function called list local devices, which I always use, which I find extremely handy. So if we run that, it should print what kind of graphics card or GPU we have access to, if we have access to one, actually. And actually, we're lucky today. So it's telling us that we have something called a device named with the index 0. And it's actually a Tesla P100, which is like I think it costs like 6,000 francs if you were to buy this. And it's one of the fastest GPUs out there. So while we weren't so lucky with the previous exercise which computer we got, we're actually pretty lucky this time. So this means that our neural network is going to be trained much faster than if we got another computer. Let's clear this output here. And so yesterday we looked at this QM7 dataset. So there's these 7,101 small molecules, which had up to 7 of these carbon, oxygen, and nitrogen atom, and then they were saturated with hydrogen. And like 5 of those molecules are just plotted here. And yesterday we talked about these features that we had introduced for these in order to handle putting some kind of conformation for a specific molecule into a vector that we can handle inside the computer. Yeah, so what I put in these 2 lines is it's 2 binary files. One contains the bag-of-bond features for each of these 7,101 molecules, and the other one contains the atomization energies of each of these molecules. So let's download those. Hopefully this will work. Yes, it worked. They downloaded both of them. And the next thing I do, so they're in this NPY format, which is a NumPy format. So I can put these directly into a NumPy array using this np.load function. So I'm doing that, and then I just want to like look at what my data is. So I'm making a histogram of all the atomization energies using this plt.hist. And I call this x_all for all my feature vectors and y_all for all my labels, all my atomization energies for each of these molecules. And what I want to program today is basically I want to program a neural network that can, given a feature vector, it can predict the atomization energy with pretty good accuracy. So now one thing we get out of here is just the histogram of the atomization energies. And one thing I can already see now that might be a problem for neural networks is that these values are sort of large and negative. And this can be a problem for neural networks, actually, because you always start with these random weights. So usually you start with numbers that are like between 1 and 0. And if you have to sum those up to like very large numbers, then that's actually difficult for the computer. So it's actually often a good idea to scale and normalize input and output features here. So we have to do that. And then the next thing we have to do is, yesterday we also talked about dividing our data set into training and validation and test set, where we can train a model on the training set, and then we could like validate the hyperparameters in order to find the best hyperparameters on the validation set, and we can go back and forth between those 2 sets. And once we were done, we would get the unbiased like benchmark of our model by training on the training set with the final parameters and then predicting the error on a test set. Yeah. So what I'm doing here is I'm just writing the numbers. I want to define my my training set. I want 4,000 of these molecules in my training set. I want 1,000 in my validation set, and I want 2,000 in my training set. So one thing I want to do just to make it easier is before I divide everything, I'm just going to scale all my heat of formations. So I'm loading in this so this HOF. So originally I uploaded the heat of formations, but then I changed it to atomization energies, but I still kept the name. So this contains this is a NumPy array that has all my atomization energies. And then the next thing I do is I calculate the mean of all my atomization energies, and I call it y mean. I also print it. And then I just divide all my atomization energies by this y mean, just to make them positive and like small numbers, hopefully close to 1 or something. The next thing I do is I put the first, so I create my training, my validation, and test set. So I put the first n train, which was 4,000. So the first 4,000 or feature vectors go into the x train. And then the next 1,000 go into the validation. And then I put the last 2,000 in the test set here. So these are my feature vectors for training, feature vectors for validation, feature vectors for test. And then I do the exact same thing for the atomization energies. So I make a training, validation, and test split of those as well, the exact same way. So let's plot everything again. So let's plot all these energies and see if our rescaling worked. Oh, I have to run this out, otherwise everything else doesn't work. And now I have a histogram of my my various splits in my dataset. So these are the target value. So basically the scaled atomization energy. And you can see the blue histogram is all my training data, and then the orange is the distribution of the training data, and the green is the test data, and finally the red here is as small as the validation part. And if you forgot what this bag of bond representation looks like, yeah, I'm just printing from the X train. I'm just printing the representation with index 1 here. And it's kind of ugly. So it's basically just a vector. I guess it's kind of hard to see when I zoom out that much. Let's zoom a little bit like this. So it's basically, it starts here and you can see it ends here. So it's a vector, and I print the length of the vector, and it's 465. So it's just a vector of some 465 numbers that we can put into our neural network. Yeah, let's close this. So let me zoom back in, so hopefully you can see it better. So I basically wanted this to be a deep learning exercise. So I'm our architecture, I'm sketching this this way. So we start with our input layer here, and each value of the input layer will come from, this will be the first, come from the first index in our representation, second index in our representation, or second in our feature vector, and so on. So basically the first layer is going to be 465 long. So I didn't print this to scale, honestly. The next layer will be a hidden layer. Everything is fully connected, and here you can see I put the arrows in, and it will be a hidden layer of some size, and then it goes into another hidden layer, and then basically we can sum up what comes out of this hidden layer in the end. And now that we have four layers, including the input and output, then this actually qualifies as a buzzword that we're aiming for. So this is actually deep learning on GPUs. And to implement all these, we have to implement the linear operations, the sum operations of everything, and we have to implement the sigmoid functions and everything for all these layers. Fortunately, we have we have something called PyTorch, which is a framework for defining all these in Python, where everything is basically building blocks that you can use to easily define architectures like this. So maybe this is not the best or the optimal architecture for this problem, but it is very similar to the one that we used in the NumPy exercise before. So I think this will be really illustrative if we use this. Okay, so let's look at some PyTorch code for implementing this architecture. So you input PyTorch, you import it by saying import torch. Just a sec. And Torch has a module called nn. So the convention is to import torch.nn as nn. And just like before, we made a class called model, or we made this function called model. PyTorch is what you call object-oriented, so it's a different way of programming Python that we haven't gone into depth with here. But basically, you define, instead of just having function, you define something called objects. So it's basically an object that has some functionality built into it. And this, we're just going to call it neural net because we're making a neural net. And if you put in a parenthesis an intent module here, you'll get some additional functionality that you inherit from this NN module in Torch. So we need some kind of, so this is actually very similar to, if you remember in scikit-learn, we imported the kernel-rich regression objects, and we imported, I think, linear regression and the centroid, nearest centroid classifiers and stuff. So this is an object that works exactly the same way. Okay, so our object, it has some parameters. So basically the input size and the hidden size, and so the sizes of the various layers. And now we can define the operations that happens between the layers here. So you basically, if you call it self, that's something that means that you store it in the same object when you make that object. And you can see here, I have a linear layer. Maybe I can, if I zoom out a little bit, I can have both the drawing and the code at the same time. So I have a linear layer connecting my input layer and my first hidden layer. And so it basically needs to know two things. It needs to know the input size and the hidden size of the first layer. And then similarly, we have also a linear operation going on here. So obviously that will have the dimensions of the number of nodes in the first hidden layer and the number of nodes in the second hidden layer. And finally, we just want a single output node. So we have what we call hidden size 2, and we have a 1 here because we just want to sum up into 1. So this is the definition of the layers. And then the second definition we need to use. So you remember this nomenclature we call the forward model when we put something in and we get the result out. So to do that, we basically have to apply the activation functions to each layer. So here you can see the first set of operations I call FC1 here, self.fc1. So we can basically say, okay, if we make this forward function and it gets the input x, the first thing that happens to x is that it goes through a linear layer. And then, so this function, and then what comes out of this function, to that we apply this sigmoid function, which is stored in torch.sigmoid. And there's also torch that basically all the other activation functions we used. So we don't have to implement any new code really for these. And you can see, so what comes out of this, something named x comes out, and we put that x in the FC2, which is the second hidden layer, and we apply the sigmoid function. And then we call whatever it comes out there x, and we put it into the last layer. So basically we sum up in this node what comes out, and then we return whatever is there. So this is basically the definition of our entire neural network. And yeah, this is a very few lines of code for something as advanced as a neural network, in my opinion. Yeah, so we talked about the sigmoid functions before, and we talked about the linear connections between the layers. And this time we're actually using a bias because it's already defined for us, so we don't have to like do anything extra to get that out. So so just one more thing. So since we're using a GPU, so normally when you do NumPy and stuff, everything happens on the CPU and all the data is stored in the RAM on your computer. But now we're going to use a GPU. So the first thing we have to do is actually, you have to define that things have to be moved from your normal memory to the memory of your GPU. And you also have to define what type of data. And we're using something called torch.float, which is 32-bit floating point numbers. So normally Python works in 64 bits, and we have, maybe you remember we had these, there's like 16 significant digits in numbers in Python. So unfortunately, GPUs, they don't work as well with or as fast with 64 bits. So normally people only use 32-bit or even 16 or 8 bits sometimes. But this torch to float is 32 bits. The next thing we do is specify which device we want to run on. And we saw in the beginning that it was called 0, and then the specific name is called CUDA 0. CUDA is it's basically the set of it's the NVIDIA set of like everything that drives computations on GPUs. So this is just the name of the device and the address for that. And what we have to do is, so we have these X train and Y train, and these were NumPy arrays. So we have to do a bunch of things for them. So we have to say torch from NumPy. So we basically convert this from a NumPy array to a PyTorch array. And the next thing we have to do is to send them to the GPU, so send them to the device via this .to function here, and tell them that on the GPU they should be of this specific type here. So this is not really difficult code. It's just some householding. You just have to like do all this tedious code to do this on a GPU. So I'm moving basically X, Y, my training, XV, YV, my validation features and labels, and XS and Y is my test features and my test labels. So I'm moving those to the GPUs and I'm reshaping it so everything should be in the correct set of dimensions here. So let's run this. Oh, what? Oh, we forgot to run the model here. So we never imported torch. So let's try and run this again. Okay, so now we move all our data to the GPU on our the cloud computer that we're running on. So before we can optimize the neural network and like fit all our weights, we just have to set all the parameters to the correct value. So the input size, that was the dimensions of our bag of bonds feature vector. So we set that to 465. And I just play around a little bit, and it seems like a good values for the first hidden layer is 30, and a decent value for the second hidden layer is 5. So we can basically define our model now. So just like we did with the kernel-rich regression objects and the classifiers, we basically make something we can call it model, which are object, and we spawn that from this neural network class that we defined earlier with the 3 parameters that we just set here. Now, the last thing we have to do is we have to also send this model to the GPU. And again, we just use this .to device here. Yep. And one thing I like to do before I do anything is just check my parameters. So this model, it has a function called .parameters, and it gets that just because we made it PyTorch. This inherits from PyTorch. So this model will also inherit everything that these PyTorch neural networks do. And one of them is this parameters, which basically prints the parameters. So let's run this. So I say param for param in model parameters, print the shape and print the parameter. So now we should be able to see if we got the right numbers. So you can see the first set of parameters, it's something of the dimension 30 by 465. And yeah, let's go up and look at here. And you remember the input vector was 465, and the next layer we defined as 30. So basically those are all the weights, the pairwise weights between all these nodes. And the next thing you see here is that there's a set of parameters which is 30 of size here. And that's the biases. Those are the B values that we add to the second layer. And the same way we have, so these are the values of the initial random values of the biases. And then we have, again, some weights. This is a matrix of 5 by 30. So that's between the first hidden layer and the second hidden layer. Some random weights here, and then the biases for the second layer, and so on. So you can see there are quite a few parameters in this neural network. Yeah, and also to optimize the weights, we also need to define a loss function, of course. So for y equal sine x, we minimize the square error, but we could also have minimized this is a mean absolute error, which I found to work better for this experiment. It's also sometimes called the L1 error, because this is the L1 norm of the difference. And then also we need to choose an optimizer. So I'm sure everybody who followed Guido's course are experts in all the various optimizers there are. One that is often used for neural networks is called ADAM. And it's basically, all you need to know is it's basically a gradient descent optimization. So you basically just calculate the gradient and you just follow it downwards until you reach some kind of convergence threshold. What ADAM is special about ADAM compared to other gradient descent optimizers is that this can handle, like, if you have, let's say you have like 1 billion training points, so that you cannot fit all of them, for example, in memory, then you can like do batches. And there are some ways to handle that, so you don't have to necessarily keep everything for your loss function memory at once. Yeah. So fortunately, loss functions are also a part of Torch. So in this NN thing we import for PyTorch, there's of course something called L1 loss, which implements this error here. And also, of course, the optimizer is also built in. So the optimizers, they reside in something called torch.optim. And all the optimizers need is it needs to know what our parameters are. And then there is this variable here called LR, which is the learning rate. So basically, the learning rate is how large step each optimization cycle you do. And you have to be a little bit careful with this, because obviously if you take, let's say you have some kind of sloped function, and if you take 2 large steps, you will never reach something that is close to the minimum. And if you take 2 small steps, then like you'll never, you might minimize your function, but you'll never reach a minimum of your function. So this is something that basically becomes the hybrid parameter of your model that you have to optimize also in principle. Okay, so let's write the optimization procedure here. So the first thing, let's just like remember what we normally do. First, we make predictions for a training set, and then we calculate the loss function for a training set, and then we calculate the gradient of the loss function with respect to the parameters, and then we pass all that information to the optimizer, and the optimizer takes a step in the direction that is suggested by the gradient, and then we go to 1 again, and we do this until we don't want to do it anymore. And for example, we can do all these operations for example, 30,000 steps, or we call them epochs actually in neural networks. So the difference between an iteration and an epoch is an iteration is like when the optimizer takes a step, but an epoch means that you took your entire data set, put it through your optimizer, and did a forward and a backward sweep of your model. So this takes about 30 to 60 seconds on Google Colab. So let's just go through the code here before I run it. So I say for epoch in range 30,000. So I want to do 30,000 of these macro iterations. And we have model, and we implemented this forward model, which was go through all the layers and the activation functions with the input. We store that in something called yPredicted. The next thing we do is we define the loss function. So here loss fn was our loss function, which we defined earlier as the L1 loss function. the root, or that was the mean absolute error. And to that function, we give the predicted labels and the true labels, and that is what we call the loss. And now here is where the sort of like magic happens in PyTorch. So all these objects basically know of each other because they depend on like the parameters and things that were implemented before. So what happens is you can actually just say optimizer. So this is just something you have to do. You have to zero out the gradient. So it starts with the gradient from 0. And then basically you can just, if you want to differentiate and take the gradient of your entire neural network, you can just say loss step backward. And this actually calculates the gradient of the loss function. Yeah, then you take a step with the optimizer. So if you're a little bit confused on how all this works, so maybe you remember Guido talked about automatic differentiation, and he mentioned something called autograd. So it was basically a way for mathematical objects in the computer to be able to apply the chain rule automatically for mathematical constructs and that are implemented in such object-oriented stuff here. So the good thing is we can, even though these are kind of complicated operations, they're actually really simple to implement yourself. I think that's a take-home message here. And then another thing I do is I just, for each of these epoch, for every 1,000 epoch, I calculate the mean, the root mean square deviation, and the root mean square, or mean absolute error and such. And so I print the mean absolute error for the training set, root mean square error for the training set, and the same two things for the validation set. And I print those here. So I don't think we need to go through this code because I think you'd be able to do this yourself. So what we expect to see is that the error is minimized for our training set, and hopefully it'll also simultaneously be minimized for the validation set. That's what we're hoping to see because, yeah, that's basically the goal. So let's run this. And oh, it seems like we forgot to run this cell first here. Yeah. Yeah. Now you can see because we start with random weights. So it has like 1,500 mean absolute error in kcal per mole. And as it optimizes, this becomes lower and lower and lower and lower. And as you can see, this actually goes pretty fast because we were lucky and we got a fast GPU. So this is almost as fast as it was to train a machine learning model for a sine of x. Yeah, and now you can see basically, I didn't make any strict convergence criteria or something. I just said run for 30,000 epochs, and that's what happened here. And we get down to a mean absolute error of about 4, and mean squared error of about 4.5 for the training set. And obviously, the error will be lowest for the training set, and the validation set is basically just to keep track of what would this probably be on the test set. And then we could, like, for example, go back and change the regularizer, or we could change the hit layers and stuff. And then we could hopefully find something that could make this better here. Okay, so one of the last thing I'm going to do is, maybe I'll write this in a better way. What I basically want to do is I want to calculate the test error. So basically y_pred. So the predicted values of y's for a test set. And what I do is I run XS was our NumPy array or it was our array of features for the test set. So I can basically just run that through our model, just like we did the forward model here. So if we run that, let's just do that. And then if we do that, we also want to send it to the CPU, and we want to convert it back to NumPy arrays, and we want it just to be a 1D array. And the last thing we want to do, if you remember in the beginning, we scaled everything down by the mean y value. So of course we want to scale everything back again. So that's this horrible train of function calls that I'm going to append here. And the same thing for the true values. We stored those on the GPU. We call them YS. So we also have to send them to the CPU, detach them from for PyTorch and move them back to NumPy, and then flatten them and scale them back by the mean of the data set. So let's run this. And so I'm printing them here, the two. And you can see, for example, the first, that's really good. These are really close. And the next one, these two are further apart. But yeah, there's definitely correlation. And you can see the mean absolute error is about 7. And the root mean square error is about 10.3 here. So let's, for example, try and plot the correlation here between the two. So for every dot here, that's corresponds to a point in our test set, and the x-axis is the true atomization energy, and the y-axis is the predicted atomization energy. And you can see the linear correlation seems to be really, really good, actually, for this neural network model. Yeah, so I think this was the entire, basically the entire coding part of this. So just a note on hybrid parameters and optimization. So basically to have the best performing neural networks, so you could probably get this error down from 6 or this 7 and 10 if you tweaked your neural networks a lot. Basically, you have to try and adjust the number of hidden layers, for example, and the hidden layer size. And also you could try the type of loss function. You can change the optimizers. And you can, for example, change the learning rate. Maybe you could get further down with a better learning rate. And also, for example, regularization. And one thing I didn't put in here, you could also like try different activation functions. Basically, there's a huge parameter space of things that you can like try and optimize for. And that's the reason why it's important to both have your training error and also the validation error, because the validation error is the one that you essentially want to use to minimize hybrid parameters for or other model parameters. And just in case you're wondering how we could have added regularization to the loss function here, so we did this without regularization. We could basically just have set for if we can make some kind of regularization level, and just like we printed all the parameters by saying for param in models.parameters to the value of loss, we could just have added, like there's a function called torch.norm. So you can take the norm of each of these parameters and you can multiply that by something. And because everything is in PyTorch, this would also give us the gradient automatically. So we actually wouldn't have to put any additional code in to get the gradient and to optimize it. Yeah. Okay, so I think that we're basically at the end of this lecture. So let me know if you have any questions. I just have one more thing to say. Let me just find that here. Just hang on for a second. Here, so just before I run off today, I just want to give you some resources. Maybe I should also post these in the chat. These are some links that really helped me in understanding machine learning and stuff. So the first one is an online course for machine learning. It's called Machine Learning Basics, and it's basically videos and Google Colab demonstrations of basically every type of machine learning you can think of. It's located on this site. It's highly recommended. The next one is called Keras, which is a high-level API for something called TensorFlow. TensorFlow is a framework that is closely, it's not related to, but it has the same kind of capabilities as PyTorch. And what Keras does is just, it makes it even easier to write things. And you can, for example, With Keras, you can immediately download, for example, the architecture of this VGG16 image recognition neural network, and then you can like retrain it to like, I don't know, recognize your own pets or something really easily. So this is something that you can use if you're interested in doing your own deep learning to actually very quickly write some very advanced applications for. And the last thing is just, I just want to give you the link to the tutorials for PyTorch, which was the framework that we used today. Yeah, so if you want to know more, go to this website if you want to look further into PyTorch. So I think that was all for today. So unless there are any questions, I'm gonna say thank you for listening to me for the past 3 days. Well, thank you for listening to me. And this is the end of the lecture.